Kerberos is a computer network authentication protocol which works on the basis of tickets to allow nodes communicating over a non-secure network to prove their identity to one another in a secure manner. Its design is aimed primarily at a client-server model, and it provides mutual authentication. Both the user and the server verify each other's identity. Kerberos protocol messages are protected against eavesdropping and replay attacks. Kerberos builds on symmetric key cryptography and requires a trusted third party, and optionally may use public key cryptography during certain phases of authentication. Kerberos uses UDP port 88 by default. History and development: MIT developed Kerberos to protect network services provided by Project Athena. The protocol is based on the earlier Needham-Schroeder symmetric key protocol. The protocol was named after the character Kerberos from Greek mythology, which was a monstrous three-headed guard dog of Hades. Several versions of the protocol exist. Versions 1-3 occurred only internally at MIT. Steve Miller and Clifford Newman, the primary designers of Kerberos version 4, published that version in the late 1980s, although they had targeted it primarily for Project Athena. Version 5, designed by John Cole and Clifford Newman, appeared as RFC 1510 in 1993, with the intention of overcoming the limitations and security problems of version 4. Authorities in the United States classified Kerberos as auxiliary military technology and banned its export because it used the DES encryption algorithm. A non-US Kerberos 4 implementation, KTHKRB, developed at the Royal Institute of Technology in Sweden, made the system available outside the US before the US changed its cryptography export regulations. The Swedish implementation was based on a limited version called eBones. eBones was based on the exported MIT Bones release based on version Kerberos 4 patch level 9. In 2005, the IETF Kerberos Working Group updated specifications. Updates included encryption and checksum specifications, advanced encryption, standard encryption for Kerberos 5. A new edition of the Kerberos v5 specification, the Kerberos Network Authentication Service. This version obsoletes RFC 1510, clarifies aspects of the protocol and intended use in a more detailed and clearer explanation. A new edition of the GSS API specification, the Kerberos version 5 Generic Security Service Application Program Interface Mechanism, version 2. MIT makes an implementation of Kerberos freely available, under copyright permissions similar to those used for BSD. In 2007, MIT formed the Kerberos Consortium to foster continued development. Founding sponsors include vendors such as Oracle, Apple Incorporated, Google, Microsoft, Centrify Corporation and Team F1 Incorporated, and academic institutions such as the Royal Institute of Technology in Sweden, Stanford University, MIT, and vendors such as CyberSafe offering commercially supported versions. Microsoft Windows 2000 and later uses Kerberos as its default authentication method. Some Microsoft additions to the Kerberos suite of protocols are documented in RFC 3244. Microsoft Windows 2000 Kerberos change password and set password protocols. RFC 4757 documents Microsoft's use of the RC4 cipher. While Microsoft uses the Kerberos protocol, it does not use the MIT software. Kerberos is used as preferred authentication method. In general, joining a client to a Windows domain means enabling Kerberos as default protocol for authentications from that client to services in the Windows domain and all domains with trust relationships to that domain. In contrast, when either client or server or both are not joined to a domain, Windows will instead use NTLM for authentication between client and server. Unix and Unix-like operating systems. Many Unix and Unix-like operating systems, including FreeBSD, Apple's Mac OS X, Red Hat Enterprise Linux, Oracle's Solaris, IBM's AIX and ZOS, HP's OpenVMS and others, include software for Kerberos authentication of users or services. Embedded implementation of the Kerberos v Authentication Protocol for client agents and network services running on embedded platforms is also available from companies such as Team F1, Incorporated. Protocol description: the client authenticates itself to the authentication server, which forwards the username to a key distribution center. The KDC issues a ticket granting ticket, which is time-stamped, encrypts it using the user's password and returns the encrypted result to the user's workstation. This is done infrequently, typically at user logon. The TGT expires at some point, though may be transparently renewed by the user's session manager while they are logged in. When the client needs to communicate with another node, the client sends the TGT to the ticket granting service, which usually shares the same host as the KDC. After verifying the TGT is valid and the user is permitted to access the requested service, the TGS issues a ticket and session keys, which are returned to the client. The client then sends the ticket to the service server along with its service request. The protocol is described in detail below. User client-based logon: a user enters a username and password on the client machines. Other credential mechanisms like PKINIT allow for the use of public keys in place of a password. The client transforms the password into the key of a symmetric cipher. This either uses the built-in key scheduling or a one-way hash depending on the cipher suite used. Client authentication: the client sends a clear text message of the user ID to the AES requesting services on behalf of the user. The AES generates the secret key by hashing the password of the user found at the database. The AES checks to see if the client is in its database. If it is, the AES sends back the following two messages to the client. Message A: client TGS session key encrypted using the secret key of the client user. Message B: ticket granting ticket encrypted using the secret key of the TGS. Once the client receives messages A and B, it attempts to decrypt message A with the secret key generated from the password entered by the user. If the user-entered password does not match the password in the AES database, the client's secret key will be different and thus unable to decrypt message A. With a valid password and secret key, the client decrypts message A to obtain the client TGS session key. This session key is used for further communications with the TGS. At this point, the client has enough information to authenticate itself to the TGS. Client service authorization: when requesting services, the client sends the following two messages to the TGS: message C, composed of the TGT from message B and the ID of the requested service. Message D, authenticator, encrypted using the client TGS session key. Upon receiving messages C and D, the TGS retrieves message B out of message C. It decrypts message B using the TGS secret key. This gives it the client TGS session key. Using this key, the TGS decrypts message D and sends the following two messages to the client. Message E, client to server ticket encrypted using the service's secret key. Message F, client server session key encrypted with the client TGS session key. Client service request: upon receiving messages E and F from TGS, the client has enough information to authenticate itself to the SS. The client connects to the SS and sends the following two messages: message E from the previous step. Message G, a new authenticator, which includes the client ID, timestamp and is encrypted using client server session key. The SS decrypts the ticket using its own secret key to retrieve the client server session key. Using the sessions key, SS decrypts the authenticator and sends the following message to the client to confirm its true identity and willingness to serve the client. Message H, the timestamp found in client's authenticator +1, encrypted using the client server session key. The client decrypts the confirmation using the client server session key and checks whether the timestamp is correctly updated. If so, then the client can trust the server and can start issuing service requests to the server. The server provides the requested services to the client. Drawbacks and limitations: single point of failure, it requires continuous availability of a central server. When the Kerberos server is down, no one can log in. This can be mitigated by using multiple Kerberos servers and fallback authentication mechanisms. Kerberos has strict time requirements, which means the clocks of the involved hosts must be synchronized within configured limits. The tickets have a time availability period, and if the host clock is not synchronized with the Kerberos server clock, the authentication will fail. The default configuration per MIT requires that clock times are no more than 5 minutes apart. In practice, network time protocol daemons are usually used to keep the host clocks synchronized. Note that some server may return a ʻkɛərbərəs result containing the encrypted server time in case both clocks have an offset greater than the configured max value. In that case, the client could retry by calculating the time using the provided server time to find the offset. This behavior is documented in RFC 4430. The administration protocol is not standardized and differs between server implementations. Password changes are described in RFC 3244. In case of symmetric cryptography adoption cryptography, since all authentications are controlled by a centralized KDC, compromise of this authentication infrastructure will allow an attacker to impersonate any user. Each network service which requires a different hostname will need its own set of Kerberos keys. This complicates virtual hosting and clusters. Kerberos requires user accounts, user clients and the services on the server to all have a trusted relationship to the Kerberos token server. Kerberos cannot be used in scenarios where users want to connect to services from unknown and trusted clients, as in a typical internet or cloud computer scenario, where the authentication provider typically does not have knowledge about the user's client system. The required client trust makes creating staged environments difficult. Either domain trust relationships need to be created that prevent a strict separation of environment domains, or additional user clients need to be provided for each environments. See also: Single Sign-On, Identity Management, SPNEGO, S-Key, Secure Remote Password Protocol, Generic Security Services Application Program Interface, Host Identity Protocol, List of Single Sign-On Implementations, References. General RFCs, RFC 1510 the Kerberos Network Authentication Service, obsolete, RFC 1964 the Kerberos version 5 GSS API mechanism, RFC 3961 encryption and checksum specifications for Kerberos 5, RFC 3962 advanced encryption standard encryption for Kerberos 5, RFC 4120 the Kerberos Network Authentication Service, current, RFC 4121 the Kerberos version 5 Generic Security Service Application Program Interface Mechanism, version 2, RFC 4537 Kerberos Crypto System Negotiation Extension, RFC 4556 Public Key Cryptography for Initial Authentication in Kerberos, RFC 4557. Online Certificate Status Protocol Support for Public Key Cryptography for Initial Authentication in Kerberos, RFC 4757 The RC4HMAC Kerberos Encryption Types used by Microsoft Windows, obsolete, RFC 5021 Extended Kerberos version 5 Key Distribution Center Exchanges over TCP, RFC 5349 Elliptic Curve Cryptography Support for Public Key Cryptography for Initial Authentication in Kerberos, RFC 5868 Problem Statement on the Cross-Realm Operation of Kerberos, RFC 5896 Generic Security Service Application Program Interface, Delegate if approved by policy, RFC 6111 Additional Kerberos Naming Constraints, RFC 6112 Anonymity Support for Kerberos, RFC 6113 A Generalized Framework for Kerberos Pre-Authentication, RFC 6251 Using Kerberos version 5 over the Transport Layer Security Protocol, RFC 6448 The unencrypted form of Kerberos 5 ʻkɛərbərəs message, RFC 6542 Kerberos version 5 Generic Security Service Application Program Interface Channel Binding Hash Agility, RFC 6561 Time Password Pre-Authentication, RFC 6649 Deprecate DES, RC4HMACEXP, and other weak cryptographic algorithms in Kerberos, RFC 6784 Kerberos options. For DHCP v6, RFC 6803 Camellia encryption. For Kerberos 5, RFC 6806 Kerberos principal name canonicalization and cross-realm referrals, RFC 6880 an information model for Kerberos version 5, further reading. External links, Kerberos Consortium, Kerberos page at MIT website, Kerberos working group at IETF website, Kerberos sequence diagram.